Hi everyone, it's Mrs. T Chem Talk Regents Chem. This is going to be a quick video on half-life because I'm not going to be in school, so this will stay up on YouTube. So if you didn't see this one in class, that just means that I wasn't absent for this and you're lucky, but I am going to be doing this in the 2018-2019 school year because of the fact that I'm going to be absent on the day of the lesson. So again, I'm Mrs. T. I teach chemistry at Calhoun High School. So the first thing is just a quick definition, is that the half-life is defined as the amount of time it takes for half of a radioactive sample to decay into something more stable. So up to this point, we have been doing different decay equations for different nuclides. And so, like for example, if we were going to talk about cobalt 60, remember that's cobalt with a mass number of 60. On table N, it says that it undergoes beta decay, which means that it gives off a beta particle and then transmutes into something else. So it's going to give off a beta particle and then turn into something else that also has a mass number of 60. So I'm just going to give you a second to look up cobalt's atomic number. Hopefully you found on your reference table, on your periodic table, that cobalt has an atomic number of 27, which means that when it releases a beta particle, its atomic number actually goes up by 1 to 28, because remember, 60 is my total on this side, so that means that 0 plus 60 has to equal the same number. On the bottom, my atomic number over here is 27. That means that these two numbers have to equal 27, which makes the new atomic number 28. So I'm just going to get this messy stuff out of the way. And what that means when you look up on the periodic table, remember you look it up based on the atomic number, and nickel is atomic number 28. So this is what we've been talking about. Radioactive nucleus, which is unstable because of its neutron to proton ratio, decays or spits out radioactive particles. In this case, it was a beta particle when you looked on table N for natural nuclear. And then after it gives that off, it turns into a nucleus of a new element. And because we have one atom, an atom of one element turning into an atom of a different element, this is also called transmutation. And because it happens spontaneously or on its own, where there is only one species before the arrow, we call this natural transmutation. So for half-life, we are talking about this natural transmutation. We're talking about the amount of time it takes for this natural transmutation to happen. And half of the atoms that were cobalt 60 would turn into atoms of nickel 60 in one half-life. Now this half-life stays constant regardless of conditions. Oops, sorry about that. This half-life stays constant regardless of conditions, which is why we can use half-life to determine the age of a sample in radioactive dating, because the half-life never changes. So again, for example, cobalt 60 decays by beta decay. So during every half-life period, half of the remaining cobalt 60 nuclei are each releasing a beta particle and transmuting into nickel 60. At the end of every 5.271 years, which is the half-life that we found, or that we find, for cobalt 60 on table N, another half of the remaining cobalt 60 atoms have decayed. So again, if we had the 60, we had the 28, oops, sorry, wrong one. We had the 27 down here, and this was the 28, and this was the 0 over minus 1e in the way that we write it. But cobalt 60 turns into nickel 60 by giving off a beta particle. So again, if we're talking about this cobalt 60 and this nickel 60, initially this is going to be all cobalt 60. So here, half of it remains cobalt 60, half of it has turned into nickel 60. Here, a quarter of it is cobalt 60, and 3/4 of it have turned into nickel 60. Now we have 12.5%, and this is all now turned into nickel 60. And what you notice is that the cobalt 60 doesn't just disappear. It just little by little turns into another more stable nucleus. And when that happens, we just keep, as the half-life goes by, it just keeps dividing in half and in half and in half every time, so that we continually get less and less of the original radioactive substance remaining. So here's another diagram sort of what we see. So if we started out with 10 grams of cobalt 60, after one half-life period, which was the 5.27 years, one half-life period, we've gone down to 5 grams of cobalt 60. That means that the other 5 grams have turned into nickel 60 and beta particles. Then after the second half-life goes by, another 5.27 years, it goes down to 2.5 grams. And the way that I write this is I say, okay, we started at 10 grams, one half-life goes by, 5.27 years. After one half-life, we have 5 grams. After 2 half-lives, another 5.27 years, now we have 2.5 grams left. If a third half-life period goes by, another 5.27 years, we now have 1.25 grams, and it just keeps going and going. And if I want to know the total amount of time that has gone by, I add the numbers at the bottom. If I want to know how many half-life periods have gone by, I look and see how many times I divided it in half. I'm going to ask you to make sure that you have out your table N, your reference table N, and I'm also going to ask you to make sure that you have out your or easy access to your periodic table for the atomic numbers if we need them on here. So just take a minute to get that out. Okay, so hopefully you have out your reference tables and you're ready to get going here. The other thing you need to get is your calculator. So please grab your calculators. I'll wait. If you're not ready with your calculators yet, please just have whoever's in charge of the video to just press pause while you do wait, while you do get your calculators, because you will need your calculators for this portion. So the first question here says, what fraction of a sample of hydrogen-3 will remain after 36.93 years? Your sheet says 36.96. Please just change it to 36.93. But the first thing we need to do is say, okay, well, we want to know how many half-life periods have gone by. So if we're going to look up, we're going to take 36.93 years, and we're going to divide by how long one half-life of hydrogen-3 is. So please just take a minute to look on table N and find hydrogen-3. Okay, so on table N, underneath hydrogen-3, it says that the amount of time, oops, not what I meant to do, hold on. Says that the amount of time for one half-life is 12.31 years. So we're going to divide 36.93 divided by 12.31 years, and we're going to say that 3 half-life periods have gone by. So again, we do the total amount of time given divided by the time for one half-life, which was found on table N. If you're not looking at table N, you can't possibly know where these numbers are coming from. Once we know that it's 3 half-life periods, we know that any total or whole original amount starts as 1 over 1. After one half-life period goes by, which was the first 12.31 years, that 1 over 1 changed into 1/2. After the second half-life period goes by, which is another 12.31 years, we now have a quarter left. And after our third half-life period goes by, which was another 12.31 years, we have 1/8 remaining. That means that the other 7/8 have turned into another atom. Hydrogen 3 decays by beta decay. So that means that it's those hydrogen 3 atoms, 1/8 of them are remaining still as hydrogen 3. The other 7/8 have now changed into the product of the transmutation. Then it says if the original sample had a mass of 68 grams, how much of the sample remains after this time? After one half-life, after 2 half-life periods, after 3 half-life periods, after the first 12.31 days, after the second years, after the first 12.31 years, after the 12.31 years, after the third 12.31 years. So we're going to go to 34 grams after the first one. We're going to go to 17 grams after the second one. And we will go to 8.5 grams remaining at the end of the third half-life. So again, total time divided by the time for one half-life, which was found on table N. Then that tells you how many half-life periods go by. The number of half-life periods means the number of times the sample divides in half. If you're still working on this question, please ask whoever's presenting the video, who's ever in charge of pressing pause, to just press pause before you move along to get to the next problem. So the next question asks about carbon-14. And again, it says how many half-life periods elapse if a sample of carbon-14 is left for 11,430 years. So you're going to have to look, this is your total time. You're going to have to look on table N to find out the half-life period for carbon-14. And the half-life period for carbon-14 is 5,715 years. So you're going to quickly do in your calculator the total time of 11,430 divided by the time for one half-life to get the number of half-life periods. So while you do that on your calculator, plug those numbers in, and you should have gotten 2. What that means is that 2 half-life periods have gone by. That means that before the first half-life period starts, we have a 1 over 1, or the whole. After the first 5,715 years that go by, we now have a half remaining. After the second 5,715 years go by, we have 1/4 remaining. So if 2 half-life periods go by, we have a 1/4 remaining still as carbon-14, and that means that the other portion, the other 3/4, have now transmuted into something else. So if the original sample had a mass of 65 grams, and we want to know how much remains as carbon-14 after that, we know, according to this problem, the amount of time that was allowed to go by was 2 half-life periods. We know that 5715 years 5,715 years went by twice. So after the first half-life, divide 65 by 2 on your calculator. 32.5 grams remains. After the second half-life, you will have the 32.5 divide by 2 again. So after the second half-life, you wind up with 16.25 grams, which is the amount that remains as carbon-14. So now, what happens to that other percentage, that 75% that is not staying as carbon-14? Well, that's what we're going to do on the next slide. So it says, what is the equation that shows the radioactive decay of carbon-14? Remember that's this. Remember this is natural. Oops, that's not how you spell natural. Sorry. That is the natural. My brain's going in different directions here. That is the natural transmutation of the carbon-14. So I'm going to give you a second here to look on table N and see if you can remember how to put in these two things. So on table N, it says that carbon-14 undergoes beta decay, right? It has the B minus. So we're going to look on table O and find out that this is the symbol for a beta particle. Carbon has an atomic number of 6. And so the top number here has to be 14 because 0 plus 14 is 14. 7, minus 1 is 6. And we look up the element by 7, and that's nitrogen. So in the page before, that means that 25% remained as carbon-14 and 75% had turned into nitrogen-14 in that problem from the page before. So the last one that we're going to do here is the iodine 131 problem. And it says that a 32-gram sample of iodine 131 has been studied for the past 24.063 days. And the first thing says how many half-life periods were studied in this time frame. So again, we're going to take the total time and put it over the time for one half-life. So please look on table N and find iodine 131's half-life. And on table N, it says that the half-life is 8.021 days. So we're going to divide the total time by the time for one half-life, and we're going to get that 3 half-life periods have gone by. And if they want to know how many grams remain, we're going to start with the original amount, and we're going to say that it goes through 3 half-life periods. And if it goes through 3 half-life periods, right, every 8.021 days, so after the first 8.021 days, remember that the sample divides in half to 16. After the second 8.021 days, it divides in half again to 8 grams. And after the third 8.021 days, it divides in half to get to our final amount of 4 grams. So after 3 half-life periods, which is how much time went by, the 32 divided in half to 16, divided in half a second time to 8, divided in half a third time to 4 grams. So hopefully that was helpful to just give you an introduction to half-life for nuclear. The presentation will remain on your Google Drive under Shared with Me, Chemistry, and under Class Notes. I've already put it there. The video of this presentation will be uploaded to YouTube for after this and will be linked to the classroom under the nuclear chapter. But for now, it's going to be somewhere that you can access. This is probably, I didn't actually upload it yet, but I'm assuming that I'm going to upload it to Google Drive so that someone in class can play it, since your school accounts will not allow you to play YouTube. So for a class presentation today, that probably was where it was found. So it's going to be uploaded to YouTube, and it's also going to be on Classroom for this day since I wasn't there. Hopefully I will be able to go back over this with you tomorrow, but when you're done watching the video, what I'd like for you to do is just flip in the packet and see if you can just do some of those multiple choice questions that are about half-life, okay?